And the screen sharing should be the right screen, I guess. Yep. Okay. Good. So, as I announced last time, we have learned as much as there was to be learned about C, and now we will start with C++, which is much more fun and also much more powerful. So for that, obviously, as usual, we create a new project. And let's begin. So, to say it in a simple way, the most important advantage of C++ over plain C is, well, there are three. One is that you can have complex objects. So in normal C, you have seen the struct, which we have used when learning about variables, and then also to create our simple list example. And this struct is just a memory block which contains a set of variables aggregated together. If you want to do something with them, you need to have individual functions that operate on these structs. With C++, you can define functions directly on the object, which is generally, from a development standpoint, much more convenient, and also allows you to structure your code in a more consistent way. There are additional advantages of using such an approach, namely that you can implement virtual functions, so that depending on which object you have, how the object was created, a different function may be available under the same function name and extend the functionality of your object. And the next important difference to see is that all the objects have a constructor and a destructor. So this is a piece of code which always runs when an object gets created and destroyed. This allows you a very high level of flexibility of implementing elements that only exist as long as their scope exists, and which get cleaned up automatically when they go out of scope. This is very helpful to develop things like smart pointers or other utilities that allow you to avoid the typical pitfalls of a normal C programming. So you can create your own structures and mechanisms to manage resources automatically, such that you don't need to remember to free memory or close some handle or alike. And the third major improvement over C that C++ has is the ability to create template functions. Probably during today's lecture we might not go as far. We will see how far we come, but just to have this said, a template function pretty much is, as the name suggests, a function which in a way acts as a template for an actual function implementation. So what here is done is that you can write a function and have a placeholder for a given type, and then you can use the one function with one name for any amount of normally completely incompatible types, as long as within the code semantic this type can be used within the function. And what then effectively happens is that multiple instances of the function will be created by the compiler in the background for each type, a different implementation, such that you can work in a way that makes you feel like it is a more type agnostic language than it really is. And this is really very useful. The entire standard template library is built with this mechanism. So we will later investigate how this works and how to use the STL in one of the later lectures. And there you will see that this template mechanism makes C++ a truly versatile language, and from the convenience of its use, not that much less convenient than not strictly typed languages like JavaScript, for example. So let's start and create our first class. Usually it is customary to create, when creating classes, to also split them like the rest of your source code into C++ and header files. but this is not strictly necessary. You could write a class only in a header file, and that would work as well. But it would of course increase your compile times. So let's create a class first using the class wizard. That should be here, class wizard. So this, though this is too complicated, let's just use the normal one. This one. We can provide a name for a class, so let's call it C my class. It is customary to start class names with C as for class, but obviously you don't need to do that. You can just start by only typing my class if you prefer that. I will stick with the C. And if you have such prefixes, it is not customary to add them to the file name. So file name would be just, in this case, my class. And you could specify here a base class. What this is, we will learn in a second. But first, let's start with our class. So as you see, the IDE has created for us already some extremely rudimentary implementation. And as you see, the files are stored kind of further apart from each other. So I find this usually not very convenient. So I just make a new folder, and then we can move them together. This is as I think much more nice to work with if you have folders where files that belong together are structured together. And now let's go to a class. So a class definition starts in a similar way like a struct definition, just that you give it the name class, and then you can give some member functions or member variables to your class. So let's start by just giving it some members. So let's say int my int, and now let's go to our test file and let's try using this class. So first thing we need to do is we need to get the class definition into our file. So we just include my class h. As you might have noticed, in the my class CPP, the my class h file is automatically included. We will use the file in a second. We don't need a body if we only have one single variable. And a important difference between C and C++ is that while in a C, for memory allocation, you are always using or are usually using the malloc or calloc function, and to free it then just free. In C++, you are using a special operator which is slightly different than normal memory allocation in as far as that it invokes certain initialization code. In this very simple example, which we are first writing, the constructor will be basically an empty function, so it will not do anything. And but let's do it. So we start with our class name, C asterisk, since we want a pointer, my class, and then we just write new and then C my class. And voila, we have created on the heap a class. We can also create a class on a stack, which is quite simple. We just don't need the asterisk, and then the class will be created on the stack memory instead. We can put this in a scope if we want. And just for maximal demonstrative purposes, let's do it like this. And here, so the object instance created on the stack within a scope will be automatically deallocated once this scope closes. So this is a very important feature that is used in a huge amount of helper classes, that whatever you define in a scope will automatically get some code executed as soon as the scope ends or terminates. While things which are allocated on the heap, so here they just keep existing, so we need to delete them manually. So we delete my class, and at this point we have created and destroyed the objects. As you might remember, we have seen the printf function in the past, so let's use it to write a few information into the console. Let's say enter main, and then here we'll exit main. We won't see much more. It will just run and create those element objects and then destroy them again. So it's a bit boring. Oh, and I forgot the new lines. And now let's try to use our class in some way. So as you see, IntelliSense is not suggesting us anything. And if we try to actually access this, like, we will see that it will not compile and it will throw an error. So this already indicates on a difference to how a struct would work. So with a struct, if you would have an int defined on it, actually we could just rename it to a struct and then run it, and then it would compile. And for such very simple elements, this is kind of the same thing. Sorry. My coughing is over. So with a class, all the members of the class are by default not accessible from the outside. With a struct, they are, and to make anything that we have in our class accessible from the outside, we need to specify which access we want. So the default access for a class is private, i.e. only functions which exist within the class can access it, while the default access for a struct is public. So since we wanted to access here my int, we just defined as public, and then everything that's below public will be treated as a variable that can be accessed from anywhere. You can then switch back to private if you want to have another variable which would be not accessible, and there is also a third type called protected. What that do we will see in a second. But at this very basic level, we will see that now we can access this variable, and our class is still not doing much interesting. So what we will try out next is we'll add the constructor and the destructor functions. These two functions, which have the exact same name as the class itself, just that the destructor has a tilde as a prefix, are invoked whenever an instance of this class is constructed. So what we can do, of course, is also we can, at least to the constructor, give parameters. So in this case, let's say int my int, and let's implement the function bodies. You might have also noticed that these types do not have a return type. So this function, this function does not have a return type. Any other function we define in C or C++ needs to have a return type. For the constructor and destructor, this is explicitly not the case. We don't even write void, we just don't write anything. And of course, inside here we can now access. So if this would be private, we here, being in the function which belongs to the class, still can access it. So this way, what I forgot, my int, my class. We have a typo somewhere. Type, it should be actually fine. My class here, class. Okay, let's see what the compiler complains about. Well, this one is clear because we haven't made it private again. And what we can do is then we can just write the argument to the constructor, and here it will also complain, so we add the argument here as well. But that is also fine. Let's just run it again. Well, it is complaining here, or it was complaining, but it didn't have a reason to do so. So it just wasn't updated. The IntelliSense was not up to date. So now, when we put some more login code, we can see when these functions will be invoked. So we just we'll add the function names here. We need to include stdioh so that we can use printf, since every include only works for the one file in which it is included. And now when we run it, you will see how this worked. So first we entered here our main. Let's make the window slightly smaller. I just need to move it. Let's put this here and this there. So we enter main. Then here we have a new, so the constructor is called. Here again the constructor of the other class is called, and then as soon as this object goes out of scope, the destructor is called, and then when we make delete, the other object is also destructed. So we can actually comment this line out, and we will see that now the second destructor will not be invoked. So at this point we have constructed a resource leak because the data are never freed. Obviously, if that application as such is terminated, then the operating system will free everything that the application has been using until that point. But if you want any stable application that can run for hours, we should not leak any resources because this can end very quickly. So what we also can do here is we can, for example, give them different numbers and then print those numbers in our code here. So my class %d, comma, destructor %d, so that we know which one is which. And now when we run it, we will see, yeah, here we need to use the variable which exists within our object. So you might also notice we don't need to refer to it in any special way. We can just directly access the variable as if it would be a local or global variable, because it is mapped into our current function scope, and now we can track which actual instance of the class here is allocated and deallocated. Is that as far clear, or do you want some more explanation about these mechanisms? Okay, no one is saying anything, so let's continue. Now, you have seen when we created the class that the class wizard asked us if we want to specify a base class. So let's do it. See my class, my subclass. Again, we remove here the C prefixes, and as base class we will specify C my class, and we specify the access as public, such that everything that is allocated on the class can also be accessed if you have a pointer or an object of the type subclass. Okay. As you see, for the most part you can create such classes yourself. The amount of code that the compiler generated is very minimal. The only difference to the before case is that here it included the appropriate header such that the other class is defined, and now here we have class public class name. So we have added a reference to the other class, and what we will now create is an object which is based on our my class but adds additional variables and additional functions and so on. In plain C, you have seen the means how a struct can be extended just by, for example, putting one struct into the other and then being able to use a pointer to the older type to just access at least the older portion of it. Here it kind of works in a similar way, just that this is made more explicit and is not necessarily that much more complicated. So let's include this other class here as well. See subclass. Again, we'll create a variable, my subclass. We call it my subclass, and we will new it with some variable, let's say 2. At this point, it is first complaining that we cannot assign a type of my class to something that is of that class, but also here is now complaining that it is lacking the constructor, at least a constructor which would take this type of argument list. So what we need to do is we need to just add some things to our class. So here I will just copy the other class's constructor and we'll add a second variable, my int2, and we can add actually two arguments that we have, int1 and int2. So in this case we could say 2, 3. now it already stopped complaining, but obviously we are still missing the function body for our constructor and destructor, so we'll quickly do it. Okay, we have created the my_int2 variable here locally, so we need of course to assign it. We could do the same thing with the okay, let's quickly build it so that the IntelliSense updates. But it's actually complaining about one thing, namely that our class here, it requires that we provide an argument. We can provide a default argument, so null, for example, and this way it will no longer complain. So if we don't provide an argument, the system will automatically just take null instead. So here now we can right, and as you see in here, we don't see my_int1. If we want to make my_int1 accessible, we have to define it as protected. Protected means that it's usually just accessible to objects which have been derived from a given object, or to other objects or functions which has been explicitly defined as a free-end object. That we'll be doing a bit later, since it adds some complexity which at this point we might not want. So now we can assign both, and since there might be cases where we don't have a default constructor, or we actually want the constructor of the parent class to do something, we can also here in the so after the constructor you can write a double point, and then you can initialize objects, like for example this class, and you can pass to it arguments. So this way so always both constructors will be invoked, but in this case it is explicit and we can pass an argument to it. And now let's of course also add some printing so that we see in which order those events are occurring. So let's copy this, change name d and %d, so that we have both my_int and my_int2. Here we will have the destructor. We need to use the variable defined on our object, and now we can run it. Not quite. We are missing a destruction here. We need to delete our other instance here. Suck. Okay, let's run. So as you see, first we run the constructor of our standalone object. Then we want to create a subclass, so effectively the compiler first invokes the base classes in constructor, and then only after that was done it invokes the second constructor of the subclass. And then when using the destructor, the things are done in the reverse order. So first the destructor of the subclass, and then the destructor of the parent class. So as the name suggests, one constructs the object, the other destroys it. And this mechanism is super useful because, as mentioned, if you have any scope and you define something on the heap, then at this point, if we put a breakpoint, we can enter the destructor, and we could use this mechanism to clean up some things that we want to get rid of. And we will be implementing such a cleanup object soon. But before we do that, we should take a closer look on how these things work. So let's create another pointer here, maybe inside my class 2. And as it's expected, we can just assign it a value from the same type. But what we can also do is we can assign it a value that belongs to a type that was derived from which it was derived. So basically in memory, a class which is derived from something has everything that the base class had plus additional stuff. So this way we can always cast in this direction and it will work fine. What we cannot do easily is cast the other way. So if we have a class which is derived and we have a pointer to the derived type, we cannot assign something of the type of base type to it, because then the expectation is that some functionality will be missing, and then trying to do it to use it will of course cause a some sort of invalid memory access. If we of course have assigned an object down, what we obviously can do is we can assign it up. The compiler won't like it, obviously. So if we make 2 here, obviously we can assign 2. But since we now know that our my class 2 contains actually this type, we can write, oops, something like this. And as you see, the compiler is complaining, but we can force it to do the conversion by providing the type. And this, of course, is contingent on us knowing that the object we are now force casting to a type, the derived type, that it actually is of the right type, so that we are allowed to do this casting. And this mechanism is in fact used by some frameworks to allow you to conditionally cast objects to derived types, including a type check, such that if you do this cast, if the cast is permissible, then it will be successful, and if the cast would not be permissible, so the object actually is just of the type base type and cannot be casted to this type, then it would give you a null pointer or throw an exception. And such mechanisms are usually implemented by means of template functions. So at this level we have not yet used our classes for much, so let's add a few more functions to them. So let's open the window. So let's here add a function int get my int. We can specify that a function is const. This means that the function will not modify any variables defined on the class itself. So this way we can ensure that if we accidentally forget it and try to modify something, the compiler will throw us an exception. So if we try, let's say, return 0, and instead we will try to assign this a value, then as you see it doesn't work. The variable is here because we can return it just fine, but we cannot alter it. We could of course use typecasting to force this to work. As you remember, const variables can be force assigned values too, although the result might be inconsistent. Here with const functions, if the variable itself is not defined as const on the class, this is quite safe, because the variable always exists as a proper variable in memory. We have just added an additional constraint on our current function. So if we want to lift that constraint, then it is fine. And there is a special keyword which we can actually use called mutable, which is kind of the opposite of const. And if a variable is defined as mutable, then we can change it even from within a const function. But let's not do that. So let's here have just our function which returns, and then let's implement the same function, or rather a similar function, on our subclass. We'll just call it getMyInt2, because its task will be to give us the second int. Here it is still complaining because we have not yet created the function prototype, but as soon as we add this, it will stop complaining. So in the code here we can printf, for example, my class 1 get my int %d, comma, I will just call it get my int. And then we'll do the same thing for our other class, just to use call getMyInt2. I have forgot to change the I did. I forgot to change this variable. Okay, and what we of course also can do is we can on this object call both functions, since the child class has all the properties of the parent class. So this works here just fine, and when we run the code, we will see that we got some. I forgot the backslash, the new line. So let's quickly fix that, then it will look better. So as you see, we could call the function and we got the expected results. If we would here cast not the right type, so for example we remove this line so that now we have the wrong type, then the code should crash, or in this case it returned garbage. So the function could be invoked on this memory region. The memory region obviously was still valid, but it contained garbage. So if we would have a more complex function, it would actually crash. But again, here you really see that C++ is a very still a very low level language, and if you are just trying to call a function which tries to access data which on your memory object don't exist, it will still do it. It will not notice that something is wrong. It will just allow you to do that. So it's important in such scenarios to always ensure that one keeps track when casting things like here and not assigning something in a way that will result in some invalid object. To quickly run it here, and now let's see how it behaves if we generate if we make another function with the same name on our object. So here let's just add getInt1, and we will change getInt1 to always return 1, 2, 3. Zack. So now when we run it, as you see, it returned 1, 2, 3, but this might not necessarily be all that we want. Also, this is kind of not the best test case, so let's quickly improve. So here we have this on these two variables. So now let's see what we have. So we have our variable of this type, then we assign this and assign it away. So here let's just copy this line, my class. That should be fine. This is of type my class. Okay, let's use this one. This is of type subclass. Okay. So, and now let's also just write one more thing. Percent p equals percent p my class suck. So what we'll now here, we will print the memory addresses of these two objects, and as you see, the addresses are the same. So effectively, I mean, this is what we expect. We have assigned the my subclass to my class, and then we have assigned the same object to our subclass too. So obviously the pointers must be the same. This is everything as expected. And if we look here, we see that getInt on this memory, on the same memory address as this invocation, gives us a different result. And the reason is that each of these objects has a different function, and the functions are not replicated with your classes. So if you have a class and some functions on a class, and then you create like 100 instances of a class, the only thing that is actually created for each of your classes is the other member variables. The functions all just exist once, and when they are getting invoked, are getting a pointer to your class passed as the first argument. So we can set up here the things such that that it will generate a more readable code to us. So we don't want any runtime checks, we don't want security checks, we don't want just my code debugging, and in the linker we do not want incremental linking. That should give us a reasonably clean code. So we can here compare those two invocations, or maybe to simplify things, we'll cache the values in variables. So int one or my int a, because it's my int 1a. That's a good name, 1a, and the other one will be b, obviously. b. Okay, and then we put a breakpoint here. We can run it, and then we'll see in the disassembly window how this is implemented. So as you see, it moves first a. Okay, it doesn't show nice names. It first puts something in RCX. So this is the first the register used for the first function argument. Since we don't have any other function arguments here, we don't see RDX being filled. But effectively, what happens here is that was it here? This is the address, and if we look what this would be, it will be the same address. Just we need to enable hex display. Zack. It should be the same address. Needs to be an address at this position. That Sorry, no, it's fine. Okay, so in the first case, if we put the pointer, it gives us directly the value of the pointer, but if we use the register plus offset, it gives us just a memory value of the stack, which then contains, which then we need to read from, and that gives us then the address of our object. And as you see, the address is the same. So whether we do this or that, so here we have the same, we have a similar code, we can evaluate it the same way. We will see we are getting again the same address. We have two different pointers, so RBP plus 10 and RBP plus 8. One is this one and one is that one. And plus 8 obviously because that's the pointer size. But they are both pointing to the same argument. And then we have a call, and as you see here, the call calls different functions. So this function lives at this address and the other function lives at that address, and they will be doing different things. And as we have seen, once we step through it, the one gives us the right result, the other one returns 1, 2, 3 in decimal. And here you already see that this is not that much different from a function that would take just a struct as a first argument. Just that here you don't need to write each time, and instead are using this arrow operator to invoke the function, and then the class pointer gets automatically put as the first argument. And the function itself actually exists just on its own. It's not strictly linked with the object. There are of course aspects to it, so if you would have a static variable on an object, then of course every function would have a reference to the same static element. We can try this a bit later, but for now you see how this behaves. So as you see, depending on which pointer we used, we ended up calling a different function, even though the function had the same name. And sometimes this behavior is desirable, sometimes it is not. So there might be the case where you would want, if you create an object and derive from the object some other object, that then you would want to be able to override a function of this parent object in a way that even if the parent object calls itself, or even if you have a pointer of the parent object type, that then if this function is called, still the actual implementation in the child will be invoked instead. And this can be done using so-called virtual functions. So here we go back to our class, and we will now just define this as virtual, and we will do the same to the constructor. And then we can, and at this level this is already all that's needed. So if you have a derived element and it sees that that in the parent the thing was virtual, it automatically applies the virtual state to the function. Obviously it is more nice to write it explicitly. And now when we run the code, we will see that no matter which of the two pointers we invoke, it will always invoke the function inside our derived child class. So if we run it, class 1, class 2, we need to put the pointer somewhere else. Let's say here, run. And now you see, no matter on which of those two objects or rather object pointers, we have invoked our getMyInt. We always effectively invoked the final getMyInt, which was implemented on the which object that we have initially created. So obviously here, if you would not use class 1 but class, then this would then give us the, in this case, 0 reply, because this is an object which does not have anything derived from it, so it obviously is printing and behaving in the way as it natively should. So this means of overwriting functions gives you a very flexible mechanism to extend existing objects. Since even if you implement a function on the object that does something, you can later just derive the object and make the function do something completely different, or a more useful scenario is do something similar yet extended in some way. So obviously what one probably would want to do is the ability to call the parent object's function, and from within your derived child class you can do it. So int equals, you first type the parent's name. So you can of course have multiple levels of inheritance. So you can have like a class derived from a class derived from another class and so on. And in this case you can, using this function, specify exactly which actual instance you want to invoke. So let's say we will just make the result to be always 1000 plus the original value. Now if we run it, you will see that it again behaves as described. And what we of course could do is could forget this, and this thing will crash. Or rather, it hangs forever and it will crash at some point. Now it crashed because it kind of called itself an infinite amount of times. So it's important to not forget to specify the parent class name if we want to do such things. Furthermore, you can, if you want to ensure that the function will be overwritten, so let's say we forgot to make this virtual. This is something that could happen. If we now run the code, you will see that it is not working. So here it's just giving us 2 because the function wasn't virtual at that point. So it failed, and there is a keyword we can use for it. Overwrite, and now it is complaining that the base class is not virtual. So now it will not compile, it will tell us that something is wrong, and then we need to go to our base class and fix it, and then we can run it. So this override keyword kind of doesn't change anything, because if it's virtual it will still override it, but it's helpful in as far as that it ensures that the behavior is as expected, because if you try to override a function which, as just demonstrated, is not virtual, then the override will not work. But there won't be an error. Only when you really specify that you want the function to override another function, then you can be sure that it will either do it or the whole thing will not compile, which is the safe situation. Better to fail in compilation than at runtime. Okay, are there any questions about these mechanisms? Is that clear so far? Okay, if no one is saying anything, then I guess everything is clear. So let's continue. We could just, for funsies, create another subclass. My third class. And it will be derived from C my subclass. Zack. Is that complete? Right, let's move the files again here. Let's a thing to note is that you don't need to explicitly create a destructor. If you just not write it, then a default destructor will be invoked and created for you. My subclass, zack, main1, main2, and now we will just move the this one here, just that we have a reason to keep everything nicely separated. And now when we specify here the parent, it doesn't matter whether we use my int or my class or my subclass. In both cases, the compiler will find the right function on the parent to access it. So if we now change our example, where was it, here, to create the third class, which we again need to include. And then when we run it, we'll again see the same behavior we already had, that both functions are overwritten and are behaving. Even though none of the pointers is of type third class, we still get the third class function to be called and do its job. So that much to this. What else would be a good thing to show you next? Functions. Let's try this protect mechanism. So as mentioned, we have here this variables which are defined as protected, so we cannot access them directly. So here, when we would try to access my int, as you see, it fails. It doesn't allow us to do it. So if we would want to change that value or access it directly, and we know there is one, but we don't have a function to access it, one common strategy is that to just create a very small class which can in fact access it. So what we could do is we can, but this is a hacky way, class. Let's just call it my third class. No, my fourth class. In this case. We derive it from something that is allowed to access it, so this is fine. I'll make a public, a public function void set my int2, let's say, int my int2. Then, or even better, let's say we want to read my int directly and not have this 1000 attached. So let's say int get my int2, my real int2, and then the function just return my int2. This also, by the way, demonstrates that you can in fact write a code directly in the class. So this we have put here, but we also could put this in the header if we would prefer that, and we can have the code. Sorry, it was the wrong header. Let's put it in this header, and we can have here some code included. So the use of this CPP files is to some extent optional, at least for simple classes. With more complex classes, you probably will have some other includes, and to keep your compile time slow, you would prefer to have those includes then only in the one file, so that if you change something, you don't need to recompile too much code. So what we'll do now is we will, let's want to retrieve the other pointer. We'll create a variable my fourth class. And what we can do is we can force cast our previous variable to it. So this cast technically is not valid, since the object has not been derived from fourth class when being created. but since our fourth class does not have any members of its own, it would not try accessing anything that it should not be accessing. So as I said, this is the hacky way. Then we just use get my was it supposed to be int1? I think it was supposed to be int1. Third class, it was supposed to be int1. Okay, so then we need to fix it really quickly. So here get my real int2 and we return int. Sorry, get my real int and we just return the real int. So now this is correct. This then we can change. We can of course assign this to yet another variable c, and then we can print it. And if we run it, we will see that we could access the variable and print it directly, simply because the class was allowed to inherit and access those members. And now the other way how such an access can be created is if we create so let's be lazy, let's create here a fourth class, sorry, a fifth class, but this time we will not make it derived from anything. Instead we will give it a constructor which takes let's say something of this type, pointer. Again, we will be lazy and put the code in here. We need give us a private own variable of that type. ptr, we will need to assign the variable. We can, by the way, assign variables here the same way we call the constructor, like this. And if we would have more variables, then we'll just write comma bar 2 0 or something. So maybe I will add here some int dummy m dummy to be consistent, just to demonstrate how one would go about initializing other variables. Okay, so obviously you could for the most part just write here is equals and this would do the same thing, but there are some differences. So if you have a class that requires a argument to be passed to the constructor for it to be instantiated, you cannot do it later, like when you would do it in the body of the constructor. You really need then to put this class here into this initialization list. And now of course this get real int, here we can, for now we can't, but we'll be able very soon. So this is what we want. We cannot do it because it's complaining, so we copy the name. Then we go to our this was of type subclass. We'll define friend class subclass, and now we have told the compiler that a class of this name should be able to access everything that is protected. So it is not like a per variable. You cannot make like a friend only for one variable. You can only make a friend for everything that's protected or not. So it's a bit limited, but for most cases this is more than enough of flexibility. And now you see here it is no longer complaining about it. So we can write a test case again here. That will be my in C number D. That was the fifth class. But now we need to either create it with new or create it on the stack. So let's go with the stack, and it will need a initialization argument where we pass to it the other variable. So as you see, while this approach here, what is it complaining about? Right. No, first of all, this should be 5, but this should not. This it has an asterisk. That should be fine. Class 2. It wants something of this, of the type of the subclass type. So since this thing is defined on the base class, then let's just go with this approach. but then of course we need to move our friend definition to the different place. Zack, here. Okay, now it's not complaining, and of course we now want to, and important, if we have something on the stack, we use the dot to access it. So it behaves in a similar way to how it works with structs. Dot for stack, and arrow operator if we have a pointer. So here we will see that the fifth class approach, let's also get real int, will give us again the real int value in this case. So you can in principle create some complex code where you have certain classes which are able to access each other's internals, while the rest of your code is not able to do so. And this is quite a useful mechanism to avoid so-called spaghetti code. So a spaghetti code is code where more or less everything is mangled with everything else, and things are accessing other things, I'm not saying randomly, but in a very unorderly fashion. So this usually is discouraged to write code in this way, since it gives for a bad maintainability of the code. So what one would want there is to have the ability to structure the code and then within reason enforce some limitations. And as it's typical with C, pretty much any limitation can then be worked around in some way, even if you would resort to a method like our class 4, where you kind of create a class without members, just for the sole purpose of accessing some internals of another class which normally you should not be able to access. This hack is completely self-contained. So for the proper way with the friend object, you needed to be able to edit the header and specify that the other object is a friend. You could, by the way, also provide here friend and then a function prototype to define one single function as a friend function, which would then be able to access this. Just as a side note. But with the, where was it? With this method, you don't need to modify the other one, so it works reliably. And of course, presumably the most elegant way to do the same without modifying the other object would be to, like here, derive it and then really use this type to construct something. So not casting in an unsafe, at least potentially unsafe way, but then really just allocate objects by using this name to create them, and then you can fully safely access anything that you might have ever wanted to access. Okay, so this much to the very basics of object-oriented objects in C++. Now let's see some functionality which has been added, and which is so it was added with later revisions of C++. It is not present in the very old C98 standards, but if you're using anything remotely modern, then you can expect to have at least C11, if not newer, at your disposal. We can check it here. So by default with Visual Studio 2022, I think, is it 2022? Yes, the default C revision is C14, which is from 2014, so it's already quite old, but you can switch to newer ones up to C20, and I think there is soon a new version of C coming out again. Anyhow, the important changes that have been introduced with this newer revisions of C++ is that normally you would need to initialize all the variables you have inside your constructor. So if you would have here, let's keep it here and add like an int 3 and an int 4. You would need to go here and initialize them with zeros, or with whatever value you find reasonable. Doesn't have to be 0, but you would need to initialize it if you don't want int 3, int 4. Where's the typo? There should be no typo. Yeah, for some reason the IntelliSense is particularly bugged today. As you see, it compiled just fine. So you would need to initialize it, otherwise the variable will have a random value, As I mentioned earlier in one of the lectures, when you have the debug built, then the value will not actually be random but a defined undefined. So we can try this actually. We can forget to do this. And then we just here somewhere run the put a breakpoint here. We created, so we put a breakpoint here. With the debugger, we can obviously inspect all the elements, and you see here that the values it got initialized for you is CD, 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 CD. But if you would use it on some non-debug build, then the memory would just contain whatever was last in the memory inside there, assuming the memory was before used by your application. Nowadays, if you get new memory from the operating system, it will always be zeroed to ensure that you don't get like a memory block from another program that might have been your banking program and there are still some pins inside or whatever. So if you get new memory from the operating system, it will be either zeroed or filled with some predefined pattern, but it will never contain data from a previous application. In old versions, in very old versions of Windows, this was differently. There you could really just get some memory and some residual data of some program that used it before that. But it's like last century sort of operating system behavior. So here, as said, we need to initialize them. So let's do it, and let's just initialize one of them. So then we will obviously see that only one is initialized, and this can be a bit annoying, since if you would create multiple constructors, so this is a thing that you actually can do. So you can, for example, here create another constructor which only initializes the first variable, or none. You could also have like one that doesn't need any arguments, so you could have 3 constructors. And what you can do, there are a few things that you can do. So the first one will be supposed to initialize everything. This one is only supposed to initialize this. And what you can do is you can chain call your constructor. So you can, instead of the constructor to the base class, you can just put inside one of your constructor a invocation of your other constructor. So let's call this constructor 2. This one will be constructor 1. It only has one variable. And the other one will be constructor 0 with none. So what you could do here, again, first of all, this will not work. So we need to give it something to initialize the 0. But what you could do here is you could also that's already you cannot simplify. So basically, if you would have a situation where you can have a where you don't want to initialize anything and then call, you could even like chain call more than one constructor as you want. For the destructor, this is not possible. You only have one, and then the other ones called are from the other objects. But as said, this is kind of not the typical way that you probably find in C++ programming books how to do it. The usual boring way would be to well, first of all, we need of course to add 2 here, so this 2 should be 0, and the 3 should be 0. So here 1 is being zeroed by the parent, so we don't care for that. Here we would still need to 0 both, and here we are setting them. Right, so this works quite fine. And as you see, you're running into a situation where if you have a very complex object, you have a lot of redundant code. So you could of course try a different approach, that in your simpler constructors you always invoke the most complex one just with a lot of zeros. This is something you could do. So this way, if you want the constructor without anything, it will call the constructor which would want both arguments, and this one will just will call this one to set the first thing. So as you see, it can already get quite complicated, but you don't need to use this method in modern C only for the purpose to eliminate redundant initializations like here, because what you can do is you can write here a initializing value. In older versions of C++, this was not possible, but in the modern one you can. And this way, when you run the code now, even though we have not initialized my int4 anywhere, it will still be nicely zeroed when we inspect it. So here, as you see, it has been initialized. And in a way, this is just natural to expect such a behavior, given that for any more complex object, it would have some constructor invoked. So you would actually expect some initialization to be done for any object, but for historic reasons, for simple variables, this hasn't been implemented. So now you have the opportunity to explicitly initialize those things. And what you can also do, which I did without explicitly pointing out, is that you can have a pointer to a class in another class, but so you can create very complex objects that contain pointers to other objects, which then contain some other pointers to other objects. You can envision it in a way like a tree with different branches being represented by different objects. And at this point, let's create yet another file, my class 6. So my class 6 on my other class. It's called my other class. That's a nice name. Zack. It won't have a base class. And in this, we will for it again create a make it public. Create a constructor and a destructor. Move the files to the same place because we like them in one place. Okay. And now what we can do is in our other class we can just include one of the other headers. For example, my third class, so that we can have everything. And now let's have a protected do I have a typo? I think it's not typo. A protected instance of my third class. Is this interesting enough? Yeah, that should be interesting. Or we go with my subclass. Let's go with my subclass directly. So we have my let's keep it with this. My third class. So you can also create objects which are not pointers inside. So it's pretty much like with the struct, where you just put another struct in it. Your class is kind of not different. It's just a memory blob which can contain your variables, and as any variable type you can also use a struct or a full other class. So when we try, you see here it is complaining that the third class does not have a default constructor. When we go to our third class, we see that it only has a constructor which expects 2 arguments to be passed to it. But here we are not passing any arguments, so we need to initialize it. So here again we'll be using the sorry, it was the wrong name. We need to copy the right name. And then we need to specify some arguments, like let's say 100 and 200. We don't make a semicolon, and then let's do something interesting with the class. Let's make a function int get int 1 and get int 2 of const. Now we can access our third class and call a function on it, just as we would expect. So a typical use case for this is that if you have a class that would represent a string, which is a very common class, one is provided in the MFC library, another in STL, and many other frameworks have their own string implementations, like Qt has QString. Simply because the normal null terminated C string with a fixed length is super impractical to operate. It's cumbersome and error prone. So pretty much every framework nowadays offers you a dynamic string which will be allocated on the heap and will automatically grow the string length as needed, so you can append until you run out of memory. This is quite convenient, and a typical use case, the most probably common use case for classes entirely being contained in other classes, at least for complex classes, is to do it with some sort of string. Another thing where you might encounter a lot of classes which are embedded into other classes, not as a pointer but really as a entire object, like here with this my third class would be a smart pointers, which we will take a look at later, which in principle are just very small simple classes which help you reference counting and deallocating elements automatically, so that you don't run into a memory leak. But with those there are also some things to be careful with, because if you use smart pointers in C in a improper way, you can still create a memory leak. So it's not a silver bullet, so to say. Unlike really memory managed languages like C#, which have a garbage collection with C, you can use smart pointers to help you a lot with memory management, but it will not be a solution that will catch every case. There will be edge cases where due to bad program design you would get a memory leak, but since these are cases which usually can be found during compile time, this is not so much of a problem. So now let's again also to this class add some more logging so that we see how everything happens, and then we will create an object of this type. Zack. Here, as you see, we do not have any arguments, so this is rather simple. Oops. Tilde here, and let's again create an object of this type. Let's create it here actually on the stack again. Put a breakpoint, run the code. Okay, something. Oh yes, we forgot to include my other class H. So okay, one more. Isn't that const? Wait, this should be const. Right. The other one obviously should have the other name, 1 and 2. Okay, so we don't care for the first part of the code here. Okay, we went a bit too far. Let's put the breakpoint here. Okay, it doesn't want to let us put the breakpoint there because we don't have enough code to do interesting things. So let's use this for something. Okay, right, now it should work. Almost. Suck. So when we remember where we are, now we make a step, and as you see, it first invokes the constructor for our my class, or rather the constructor for our my subclass 2, which then invokes the other constructor, which then invokes the my class constructor. And only once this has been finished, so once this here has been executed, only then we enter the body of our constructor here. So you can, once you are inside the constructor, expect all the objects to have been already set up which have constructors present. So you basically would only need to initialize the few variables which you have not initialized yet. And if you are using the simple way of initializing as we have shown in here, then you don't need to do much inside your constructor. And then of course when we step through it further, then we at some point step out, and then we see here that here our destructor has been invoked. Apparently I forgot some new lines again, so let's fix it really quick. Here, is it the only one I forgot? Yeah, the other ones should be fine, so let's quickly run it again. Zack, zack. Right. And of course we at some point have the destructor for this line here as well invoked once we close it. So we could also comment everything out so that it's a bit clearer of what is happening. Zack. Okay, play. So we see that destructor is first called for the outer class, then it's called for the element, and then inside, and then this one calls the destructor for the subclass. So that much about this. So do you want some more explanations of these mechanisms, or can we continue? Is it clear, or should we make a 5-minute break maybe? Well, I guess before we start with the next thing, we should make a short break. So let's continue in 5 minutes. I will turn off my mic. If you have any questions, you can ask them. I'll be listening in, and then I'll answer them instantly. Okay, the 5 minutes are over. Let's continue. So one thing we probably should take a look at is how calling the different functions looks in assembler if we take a look at how these virtual functions are implemented, because this is quite a fascinating, let's say, topic, and we haven't actually taken a look on how the compiler implements this mechanism. So let's say we have here our which one was it, subclass, and in the subclass we have this getInt2. So let's not make this one virtual. So we will have in the parent class the getInt virtual and the getInt2 being non-virtual. And at some point here we have getInt2. So let's let's quickly redo this. Log in A. And let's put it side by side. So this one is, and this one is not virtual. Okay, so let's put a breakpoint and run. And what we see is that first of all we notice two things. The normal function call, which we have taken a look at already, is much shorter. We just load the register with the object pointer, and then we call a function just by its address. So this is quite simple. But here our call to the virtual function is quite a bit more convoluted. So we are first loading something into Rex, then we are loading something from Rex into Rex again, and then only once we did this, we here load the first register for the with the object, and here we execute a call not to a fixed address, but we call whatever is at Rex +8. So we have basically some memory block which contains function addresses, and then the thing jumps to this function addresses. So you can think like, let's say, so our object itself starts at RBP. So here, as you see, we somehow again start with the object, but then after we have loaded it into Rex, the first entry in the object is a pointer, and here in this line we get the address to which the pointer is pointing to into Rex, and then this address plus a certain offset is the function which we want to invoke. So we should maybe take a look on how this looks in more detail. So I will. So one additional interesting thing about C in comparison to C++ is that you can create functions. Sorry, that you can create classes in principle within functions. So we can here, for test purposes, create a class. It's my test1, and it will be perfectly fine. So let's create an object, or let's get the size of the class in const int my typo my test1 len is equals to the size of my test1. Okay, now it should be actually 0, and is it 0? Well, it's not quite 0, but it's not. We don't really do anything, so it just allocates 1 byte as a dummy. But let's give it a variable. Let's say an integer. So int my data. Now the size will be 4. So now it actually contains this data as expected. And if we add some function, so for example, void so public set data and get data, set data and data my data is equals data string zack und int get data const on my what was it, my data Strichpunkt. The class will still remain 4 bytes because, as we said, those functions, they live once in the entire program and not in every object. They only get a pointer to this object passed to it. Okay, now to go for a comparison, let's copy this thing entirely, call it test2, and let's make the get function a virtual function. Okay, let's copy this line as well to get the size of our new object. And now you will see that it's well 16. It is 16 because it is rounded. So we could, for example, make, let's give it 2 ints. Data, my data and my temp. You will notice that the size of the first one has increased to 8, but the size here will stay at 16. Because basically what we now just did is, as you might remember from the struct, the elements are try to be aligned, and sometimes the compiler adds padding such that basically an empty field such that other fields are aligned in a way that is more helpful for the CPU to be as performant as it can be. But what we learn here is that if we have a virtual function, then the whole size of the object has been increased by 1 pointer size. So the next thing one might intuitively want to try is what happens if we will have 2 virtual functions, which you know might be a useful use case. And here we see that actually nothing changes. It still remains 16. And the reason is that when we create an object, or rather like this, let's start from this side. When we define multiple different classes, like this class and that class, and we could derive some of them from the other ones, etc. For each such class, for each such type, for all the virtual functions, a so-called jump table is created. So it is a table which has entries. So the first function has address such and such, the second function has address such and such, the third function, if we have a third function, has an address such and such, and it contains always pointers to the actual function which only exists once. And when we create an object which contains a virtual or more than one virtual function, the first entry in the object will be a pointer to one of these jump tables. So in this case, test2 has one jump table and test3 has another jump table. Or if we would want to use our existing classes, so here my class has one jump table for my class, and my subclass has another jump table for itself. And depending which of those objects we now instantiate, so when we start with my class, then basically the object gets created and it uses the jump table of my class while it's being created, and as soon as the control gets passed to this part, so to the constructor inside our derived object, it will replace the pointer with its own pointer, such that then the system will, such that the pointer in the object will now point to the new jump table. And this way, these virtual functions can be overwritten, because as soon as we try to call any of those virtual functions, as we did here, we are retrieving the pointer to the jump table which applies for this object, and then when we do the actual function call, we retrieve a function from this jump table. So this way, we for every object, no matter how many virtual functions we have, we only waste the memory per object of one pointer, and a static amount of memory one time for however many objects you have, which represents the jump table. This is a very efficient way. The downside, of course, is that it adds a few more operations to every call. Nowadays, with modern systems, the performance impact of this is negligible. If you look into very old programming handbooks and guidelines, then you might find things where they say that you should not use virtual functions unless you have to, because they have bad performance, which back then was true. Nowadays it usually doesn't matter. The things that will be a drag on your performance will not be in your program will not be the use of virtual functions or not, but other things usually. So without going into a detail there, let's just leave it at that. So we have seen how this works on a low-level aspect. If you are interested, we can, in one of the much later lectures, actually take a longer detour into this mechanism and learn how we can, if we only have C code at our disposal but a C++ object, how we can interact with a C++ object, how we can basically implement, in quotation marks, our own C++ using just C. It won't be pretty, but it will work. So the takeaway here really is that the compiler is just creating a lot of code for us in the background, but in principle everything that is done there is not in some way hidden away or abstracted such that it wouldn't be accessible. It is still there. It is still just a short hack away, so to say. Okay, one more thing that we should take a look with regard to classes is will be the more elegant ways a class can be used. So we can create here yet another class. See my integer, and let's make it public. Let's give it a constructor, int my int is equals 0. Protected int, sorry, int mint or mdata. Let's call this data. Okay. So we have now. Let's actually we could create this inside here if we wanted to. Why not? Now let's create an instance of this. So my int 1 1, my int 2 2, and one thing that you probably still remember is that the computer on a hardware level can only handle numbers which are as big as the registers that the computer has. It cannot natively handle any bigger number. And in cryptography, for example, it is very common that you would have 128-bit numbers or even 256-bit numbers or even numbers that have like 4092 bit, so which are really extraordinarily huge. And obviously the question is how one would handle such a thing. As we have seen when using 64-bit integers on a 32-bit platform, at that level the compiler can just turn any operation into any 64-bit operation that is as such presented in the code into multiple 32-bit operations, such that you can properly use your 64-bit variable. But the compiler does not implement such a mechanism for any bigger data type. So you can do this without effort only for 64-bit on a 32-bit platform. Any other case you would need to do by hand. And the way to do it properly is to create some own data type which would contain your data. So in this case we only hold one int. If we would want something bigger, then we would have, like, say, data low and data high. So let's say data L and data high, and data low, data high. Then we copy this again. For high, which wouldn't need the same name. And now intuitively one would think, okay, so you can initialize it with some values. So let's initialize. Then you'd probably have like some function, let's say myInt, which would return a something of the type myInt, and let's call it let's call it something that we can easily implement. Let's call it XOR. XOR is a operation. We have learned what it does. So here we would have a operator that takes a const reference on some other function, and then it would internally create some cint return. You can return a complex type. So we take it, then we would say, let's say data low is gleich. Now one more detail, when referring to the own variables, you can just do it directly. So is this operator then or punct data low, or you can use a special keyword called this, which in such scenarios is obsolete. So this is basically the first argument that gets passed to your function, which is hidden. And it is not needed when accessing variables, but it is useful if you, from within a function, would want to get the pointer to the object you are in right now if you want to call something else. So here we would do this operation, and then here we could have this punct XOR that, and the third one would be the result. Let's say 1, 2. So 1 XOR 2 should be 3, I think. Let's see if that's correct. Zack. And as you see, it worked out. So this would be a method how you could implement your own mathematics in more or less any way you want. But writing then your code like this is quite cumbersome. So what is available in C++ is you can create your own mathematical operators, or generally your own operators. Not all of them are mathematical, as we have seen. For example, the arrow operator or the dot operator are used to access things rather than being used to do some mathematical operation. So we can here rewrite or simplify our code. We have the same return time, and then write operator XOR. It wants the same argument, and typically, since you would have usually more than one version of such a operator, what would be the customary thing to do is to still have your function written out, and then from within your operator you just call your function. And if you have a compiler that is not in debug mode, then it will usually even optimize this away. So now, instead of writing like this, we can just XOR, and voila. We can put a breakpoint here, so we step through it. Obviously here we don't have optimization, so as you see, it loads our one register with our int, then it loads the next register with that next int, and the last register with the last int. So as you remember, the way it worked when you called a function that returned a complex type, actually the return value was not longer passed by rex, but instead a pointer to the memory where the result should be has been passed as the first argument. So in this case it is the second. So basically it's like this: the first argument is your is still your this pointer. Although wait, why is it? No, sorry, other way around. The first argument is your this pointer, mem1, int1. The second argument is then the pointer to your return value, and the third argument is, well, your actual argument. In this case, myInt2. Okay, so let's step into it. Zack. Then we obviously end up here in our function, and in a release build that will be optimized away, and then we of course end up here in our actual function body, and then we just exit from everything. So this way you could of course also write an operator for plus or an operator for minus. See my int operator plus minus for whatever you want. Obviously, not bitwise operators are a bit more complicated, because with addition and subtraction, for example, you have a carryover, so you will need to carry bits from your high to your low part, or vice versa, depending on what you're doing. So the code will be significantly more complex than just this simple bitwise operation. And of course, ideally you would create your own int object, which would not contain just a high and a low portion, but something that would contain an array of chunks, such that you can, let's say in an increment of 32-bit or in an increment of 64-bit, represent any number of any length that you might ever want to represent. So this is something that is quite useful, and for cryptography absolutely necessary. So as you might know, there is a part 2 of this lecture in the next semester, and to this there also are explicit exercises like a separate lecture. So you have 2 hours exercises and 3 hours lecture part 2. And during the exercises next semester we will implement such a myInt class from scratch, so that you can do your own cryptography at the lowest level possible. Obviously, for real-life application, you would just take some class that someone already wrote, but to learn how these things work, this is quite a nice way of doing it. And I think a bit advertisement for the next lecture is not out of place. So that was the message from our sponsor. Now let's return to our coding. So as you see, you can have these operators which replace the functionality of mathematical operators, and another very common operator which you might encounter when doing things, which we will be using during this lecture already for a few very simple examples, is the assignment operator. So here, by the way, you don't necessarily need one. So in this case, you have, as you see here, we are using assignment, and it works because the compiler generates for us a default assignment operator, which just copies the data over. But if you have a complex object, for example, something that contains pointers and other things, then you might not be able to just make a copy, because if you just make a copy of a pointer in some implicit way and then the other object doesn't know anything about it, it might then deallocate the pointer, thinking it was the only one that held an ownership on it, while there is a second object now. So in such scenarios you would either want to use smart pointers, in which case you could rely on the automatic copy constructor, because it will probably invoke the manual copy constructor of the smart pointer. Or what you would do is you see, okay, I have a pointer that says something, so I will make a new object of that type. I will copy the data from one pointer to the other, from one object to the other, so that now you have actually 2 objects. So this would be called a deep copy, while just copying the pointer would be called a shallow copy. And for such scenarios, if you want to have some say in how a copy of your object will be created, you can use this assignment operator. So it returns something of the same type, but as reference it's called operator assignment. Obviously, you can also use an comparison operator. You could define your own comparison operator, but this will be out of scope for the current lecture. It takes the other entry, and what then basically does is super trivial. It just assigns in this case it's super trivial, so we just emulating of exactly what the compiler would do, but a set with a more complex object, this would be more complicated. So we can put a breakpoint here, and then at some point we'll step into our assignment operator. It looks like it has optimized the code already a bit, so let's do it like this. Now we will definitely invoke this. Right, I forgot the return. And here we need this. Actually, we make asterisk this. So where we are returning something, well, as you know, a reference and a pointer under the hood are the exact same thing, just on the level of the source code they are handled differently. So if we are returning a reference, then we need to return actually asterisk disk, even though it is just returning a pointer on the rex register. So let's do it. And now we see here that we have a invocation first to our XOR operator, and then we have the invocation to our assignment operator. And now if we of course step through it, we can step over the other one and step into I stepped over it. Let's run it again. Step over, step over, step over, step in, single step, single step, single step. No. And then we end up in our assignment operator. And if we would not have it, we can autocomplete, breaking everything as usual. We see here that we have one call. It actually did not use the assignment operator. No, it moves. It's just moving here the data. So it constructed its own kind of assignment operator just by copying the data around. So we can step in here, step in there. We can, let's see how we can improve that. As an example, I don't think we can, because it's now optimizing like too much away. Well, instead of trying to tricking the compiler into optimizing less, let's just ignore that, and let's take a look on the other use case. So if we are not assigning using the assignment operator and doing it like this, we have also seen that the code was quite compact, because basically it just directly passed this to the function, and then everything was done automatically. So the next thing that you often, when using assignment operators, to be on the safe side, want to do is to provide an own constructor which more or less behaves like a assignment operator. Let's see how we can demonstrate this in a good way. So let's start with this, then let's call it for and assign from this, and if I'm not mistaken, the thing will actually default in both cases to doing the same thing. So let's okay, let's leave it like this, run it, and then inspect the code. So yeah, so as you see here, it is invoking properly our operation here, while here and there in both cases what it basically just does is it does not even create a function. It is just copying the two different data elements in one go. So since the whole object here is only 64-bit, it can even fit it into one register. We could break this by adding another variable, let's say temp. Now it will need to generate a much more complicated copy code. As you see here, now it's using this rep moves, as we have seen with our structures in the lecture about structures. So it is kind of doing a lot of things, but this could be optimized if we use our own code. And in this case, we will here create our own copy constructor, which again will just do the same thing. Zack. We could actually improve, use less code if we just write this, because we can in the assignment, in the copy constructor, just use the assignment operator. The only thing is that if the assignment operator here would need to do some code cleanup, we would first need to initialize everything to zeros or do something like that to ensure that the assignment operator will not misbehave. So if we would have a object, some complex object which has pointers to other things, and then obviously when we call the destructor, we will be deleting all the other pointers. But if we call the assignment operator and we already had some pointers, we need to get rid of all of them. So in this case, the assignment operator will need to do some cleanup. So if we would be invoking the assignment operator from a constructor, you would need first to first initialize all the things with some null values, such that the cleanup will not see any unallocated memory. So depending on the complexity of our object, it might be a good idea or not to save code by just using the assignment operator inside the copy constructor. But anyhow, let's run it again. And as you see here now, all of these lines are basically just calls to the different operators, which then internally will do what we told them to do. So that's that. Yeah, I think about operators this will be mostly everything, although not all. So as mentioned, you can use the arrow and the dot operator or the reference operator, and all these operators can also be created in a custom way, so that you can override pretty much any functionality of a C++ object with your own functionality. Even for an array, the square brackets operator is basically just a function which can be implemented by you yourself. So I think during the next lecture we can do such a thing. So we will implement some more complex C++ object that will help us to do something productive. But before we go there, we still have half an hour, so let's see what other short things we can do in that time. Right, there are a few things that we should also demonstrate. So here, let's say, though we could demonstrate it here. So instead of data high and data low, we could just call this int asterisk data, and then add int count. Then we will replace all of these multi-lines with for int e equals null, e is less than count, e plus plus, and then we just go from data from I. Then we just do it in a loop. Zack. Assignment likewise. Just the data is other. Okay. And here we of course need data 0 and data 1. Maybe 1 and 0, the order doesn't matter, but now what we need is the destructor, and we need of course to initialize our data structure. So we need to new int 2. We need to allocate the memory, and then here we will need to free the memory. So delete, zack. And let's see if we can. Right, we need the count as well. So in this case, new count is equals 2. And let's beef up our assignment operator, because in principle, while here we obviously always just create elements that have two counts. If you would have a more complex element that can have any size, then we would need, when assigning, to take a look on this. So the way well, first of all, this operator also needs that, but count should now be taken from the other one, punct count, and the rest is fine. And in our assignment operator, we will first need to get rid of what we already have. So delete data. Then we'll need to create a new data block. Then we can continue with our copying. So as I mentioned, if you would just use this trick, we could, but then we would need to first assign this to be null, such that we don't run into issues. And it's important also to note that delete from null while it might sound strange, is valid, because then the delete just won't do anything. So the way delete is implemented, it checks if the object passed to it is null, and if it is null, then it doesn't do anything. But this might not be the case in all the compilers, especially if you have some very old ones. So it would be recommended to just be on the safe side before you delete something, to just check whether it exists, in which case you then can really create something that works fine. In this case here we also need to handle another special case. So if count is not equals other count, then we will just return an empty object, because we cannot XOR, or we could throw an exception, but throwing exceptions is something that we'll take a look on in the next lecture, I think. Unless you are interested in that, or unless we are really fast with what we have here. So we could take a look on C++ exception. Half an hour might be enough for that. Okay. Okay, let's see what else would be good to show you. Yes, one more thing. As you remember with our classes, we already have some classes here. I just copy this again. With the classes, we can create virtual functions, but what you can also do is you can create a virtual function which does not have a function body. We're just doing it by writing is equals 0, and it must be virtual, otherwise it won't work. And then what you can do is you can derive from this public. Oops. And if you now create some objects, so let's implement this, then class 0 is equals new. Obviously you cannot construct anything from class 0. If you try, then it will just throw an error and tell you that it cannot create an object from an abstract type. So we need to use whichever is the first class which has every function implemented. And now on this you can call IntelliSense failing. You can call your functions. It's class public. Public is missing. IntelliSense was right for once. And such an object at this level is really just made out of the jump table itself and nothing else. And this scheme is used often when creating interfaces, which should be as compatible as possible. So you just create a empty class only with the function names that you want to allow to be callable, and then somewhere deeper in your system you would create an object which actually implements them, and between your APIs you can then just pass pointers to an object of type of your abstract type, and be reasonably confident that you will have binary compatibility, so that if you have a DLL which you built like a year ago and you have some new code, then it will still be compatible as long as you don't change the actual abstract class. So you can do whatever you want here. You can change the order of your functions, the order of your variables, whatever you want. It will still remain compatible. So this is quite a useful mechanism. And another thing that is also worth mentioning is that you can have 0a and 0b. You can have an inheritance from multiple objects at the same time. So in this case, this we will change into, so we'll create an object at class 1, then we'll have two pointers 0a and 0b. Oops. P class pointer 0a is equals, we can assign the same thing to them, 0a, 0b. And on 0a we can now only call the set function, while on 0b we can only call the get function. A, B, const, why is it complaining? B, A set, B get, B is get, that should work. Oh, that's why. Yeah, the naming should maybe be a bit more specific. So this could be like a setter, and setter, and this would be a getter. So you can create a very flexible interface, and then if you have a function somewhere, let's say void set my int, which takes int e. Okay, for this we need to move the classes out from here. Zack, and this will take a setter type. Then per setter e. So instead of setting directly, you could say 5, Zack, and have a setter function. So the mechanism is very flexible, and in fact you don't need, you are not even constrained to deriving only from abstract classes. So one of those classes could have own members, and in fact in C++ you can derive from any amount of non-virtual classes at the same time. In other languages, usually the way it works, you can only derive from multiple interfaces, and an interface basically is a class which only contains virtual members, and in addition to multiple interfaces from one parent class. In C++, as here, you can really derive from multiple fully independent fully implemented classes, and the mechanism and the system will work. So in this way it is a bit more powerful than, for example, C#. Of course that gives additional opportunities to break things, especially with typecasting, because as you might remember, the whole niceness about how you can work with objects with structs in C is that you can have like a struct which contains another struct which contains another struct, and then the first pointer will, no matter which of these types you cast, will give you the right result. While if you are inheriting from multiple objects, then only one of the objects will be the first object in your object. So only one of them you can cast to without going through some proper chain of casting and calculating offsets of your objects. So we could try this as well. So let's create some other classes. So class C my A, public int A. We will not bother with functions, variables are just as fine. C my B. Now we derive a class C my AB, public C my A, public C my B, Doppelpunkt Greta B. Yeah, we could add a variable here, but we don't really care. We can move this further down so that everything is in one place, because for this demo this is fine. So we create an object of type C my A, per B, UAB, and at this level, when we cast to A or to B, it will actually work. But we'll see that while in one case this pointer and this pointer is the same, in the other case this pointer and this pointer will actually get different numerical values. So We don't need this breakpoint. Zack. So AB lives there, and my A, this one, my A lives at the same offset, while my B gets a different offset, just shifted by 4 bytes, but different. And as long as you are kind of inheriting along one chain, then you can hardcast anything to anything, and it will in the end work out fine. So here, let's say we want to hardcast. What do we want to do? Let's set this A is gleich 1, 1, and B is gleich 2, 2. And then let's say we have here our this thing, and we want to hardcast it with another AB. AB2 is equal. So obviously, it will try with both. Obviously, the thing doesn't want to allow us to do this, so we tell it no, that's fine. We know what we are doing. Zack, and when we run the code, it complained. Right, that should be a different name. Let's call it 3. So the first one, we should disable hex display. So the first one plays out nicely, 1, 1, 2, 2, while the second one, actually it worked. Why did it work? It shouldn't have worked. That thing was somehow smart enough to do that correctly. As you see, it implemented here a lot of code. I think if we turn off runtime type information, then we will break it. All options. Enable runtime type informations. No. Let's see now. Nope, it's still did the right thing. Well, it's smart enough, so we can still break it. We can say void. So as you know, we can cast anything to void and more or less void to anything. And if we do so, as you see, it implemented a much simpler code. So here, for the first case, it still works fine. But for the second case, wait, it still worked. It shouldn't have. These two are diff. Wait, pay A, pay B. Oh, now it's kind of a tricky thing. So the thing is, at this point, if we do it with the void, it will not do anything, and then PA and PB will end up the same values. Only if we do it with the right type, the second one will be shifted so that it gets a different offset. So what we actually need to do to break it is AX, PX, and then PA, PB. So first we do the cast, such that it does the cast smartly, and then here it gives us the right offset to access the second object. And now we cast it to void, so that it loses all the type information. And then if we cast from void, so without having the right type information, now it will be broken. So now you see that A actually shows the content of B, and B is invalid. So it needs some intention to break the mechanism, but you can. And an important thing to notice here is that if you would do some extent of casting from one type to another type, yet to another type, you might lose the compiler might lose track and create such a situation that this cast would not work out properly. And it is just much simpler if the compiler just does not allow you to make to derive something from more than one non-abstract parent. And that's why in C# I guess they decided to make it this way, just simplify the work so much. But in C++ you can, and I find it actually quite useful that you can do it. There are various use cases where this is nice. And an important note here is that if you would be using a language which does not allow you to do this, what you can do always is you can include one object as a member into another object, but then of course you cannot access the functions on this object directly. So it adds some additional complications, but you can have this functionality as well. And last thing I think that is worth mentioning about classes is, as you have seen for now, the different objects which we have been using, we always created them and then at some point destroyed them. But there are various use cases where you would want to have a global object, and the way, the simplest, most elegant way to create such a global object is to define a class. Such a class is usually called a soliton because there is only one instance of it at any point in time. And what you do is you define the constructor as private, then you give a public function, and it must be static. So static means that there is only one instance of whatever is static for all the classes. The classes are sharing it. For a function, it only means that it will not have a this in it available. And will be only able to access static variables, because static variables will be like any variable which is defined somewhere outside of your functions, will be just exist in your program and will be accessible to all the functions which you have. Okay, so here, if this is null, then this is new. This, we need a body for that. The body doesn't need to do. Oops. Body doesn't need to do much. Just needs to be there, and then we return. So now the first time when you try to access this class, an instance of it will be created, and since it's a static variable, this instance will stay forever, but we still need to give the instance some place to live. So we do it kind of the same way like we define functions. We have the type and then the class and then the name. So in this case like this, equals null. This will be initialized by the C runtime when the program starts before control is given to main. And then inside main we can access any static function using the double point operator. So here let's add some non-static stuff like int counter. We can initialize it to 0. Let's do it here. Then let's int get next plus counter. So each time we call get next, we get incremented number, and as you can see, we cannot access. That should not allow us. Well, if we try to access get next, it will. Well, it showed it, but it doesn't allow us to do it because it's not a static function. So you need a static function to be able to access it with the double point operator. And a static function in turn can only access members which are static themselves, and those members need to live in some C file somewhere. It's not enough for them to be defined. But if we have our soliton and then have here our get next and x1, then we can call it as many times as we want, and we will notice that we will only for the first call arrive in the constructor. Actually, I should have put the breakpoint directly on the constructor. That would be more illustrative. So we arrive in the constructor from here. We can see it in the call stack from instance, and then we arrive in getNext, and from now on we will always arrive only here in this getNext until we are done, because the variable already has a value. Such objects are often used in programming with C++. You often have some things where you want to share an object and just one instance of it, and you know that you will never have two instances. Plus you want to have some easy way to access it, so you create such a soliton, and then you can work with it from anywhere in your code, as long as you include the right header. There is in this special implementation of this function here a small issue, namely if you would have multiple threads accessing your soliton at the same time, trying to access it for the first time. The way this is implemented here might end up in creating like two instances, which would not be good, because one of them will be returned, the other no, or even in the worst case, if you have some optimization, one call might get one instance while all the other calls will get the second instance. So if you expect that your calls to instance will come from multiple threads, you would need to implement this function here in a thread safe way. So add some locking mechanism which guarantees that there will not be no execution in parallel in two threads at the same time. But this is a topic for a different subject for a topic for a different day, or a subject for a different day. Right. Is everything clear, or do you have some questions? Okay, no questions. Then maybe let's do one last very simple thing. Classes, as you seen here, can be so you can access functions on classes using this double point operator, and you are also using this sometimes when trying to access a parent function. And there is yet another use case for this double dot operator, which are so-called namespaces. So semantically, every class for itself is a namespace, and if you have a class which is defined in another class, then you have like a namespace in a namespace in a namespace. But you can use this namespace feature independently from creating entire objects. So you can, in a very simple way, so to say, just create only a namespace. So we can maybe do it here at the very end. Maybe no. Maybe let's do it at the top, because we want to demonstrate it. So namespace, my namespace. In principle, it kind of looks a bit like a class, just it started with a namespace, but it doesn't contain anything but other things, and it does not represent an object in C. It only represents really a namespace. And in this case, you would then just type namespace, and then whatever is defined in your namespace, you can access from there. So, for example, if you would add some variable here, int my should be 0. It should be a global variable, but to access it, we need to provide namespace, and then we can access our global variable and do something with it. The namespaces don't in any way translate to machine code. These are only made to allow you to reuse names if you would really want. So we can create here my other namespace, and here we can create the same variable, and the system is completely fine with it, because to access this variable from anywhere else, you need to use the different namespace. So this one will be set to 2. You can also prove it by just running the code, and then you see this one is 1, and this one before we set it is 0. So they're really, despite that they have the exact same name, they do not exist together. And yet another nice feature is that, like with classes, if you are inside a class, you can access all the variables that are defined on the class when you're in a namespace. You can access whatever is in the namespace directly. then of course to access this you will then still need to use the namespace name. So, and of course what you also can do is you can put one namespace into another namespace. Let's call it just my. And I drop the my from here. Okay, now we need my namespace. So you can, in principle, isolate parts of your code name-wise, basically namespace-wise, from each other at as many levels as you want. This is used by very large projects quite often because people, if they don't communicate all the time, then they might choose to give to something the same name, and then you would end up with having name conflicts, and then one of the big parts of the project that needs to work together would then need to rename everything, so this would not be a good user experience. And this STL library, which I mentioned already a few times, it in fact is using an own namespace, the standard STD namespace, and there inside all the things have really simple names, like a list is just called list. So it is very conceivable that if you are writing your own code, you might want to write a list somewhere just as a variable name, and then this would fail because the word list is already used as a class name in the STD namespace. But since it is a namespace, then it will not conflict, because you would need to prepend your because to use the STD list object, you would need to prepend the STD namespace name. And one last thing you can do with a namespace, if you would know, okay, there will be no naming conflict and I'm too lazy to type the namespace all the time, what you can do is you can say using namespace my in this case, and then as you see it's not longer complaining because it imports everything from the my namespace into wherever you are right now, which for my worked. We could use now using namespace other namespace, which means this works. And now let's do this. And now it doesn't work anymore. Now it is complaining that it's ambiguous. It doesn't know from which namespace it should take it. But if we do it like this, so if we are using a namespace and we are in a namespace, we can specify still a more specific namespace. It's kind of like with the classes and the derived functions, that if you want the parent function, then you, instead of using the name of the function, use the name of the parent class plus the function in the parent class you want to call, and this way you make it explicit what do you want. In case of classes, the inheritance gives you a certain hierarchy automatically, so you don't get an ambiguous issue if you call a function which is derived in the child and in the parent. But here, if you just add namespaces, then you will run in such a situation because they will not be prioritized, let's say, on their order or anything. It will just say it's ambiguous, and then you need to extra specify it despite the fact that you have in principle provided all the information needed. As you see for the getInt, which only exists in one of the namespaces, the system is smart enough to figure out which one to use. So this issue really only arises if both namespaces would then contain competing names. And since we are running out of time, I think this is a very good point to finish for today. If you have any questions, you can ask them. If you want to stay longer and ask questions, that's fine. Other than that, you can of course send me questions by email or ask the questions during the next lecture. That's highly encouraged. In the next lecture, we will, I think, create a own utility class that will represent a safe array. So an array which does not allow us to access an invalid offset, as we have seen in the last in one of the last lectures when we learned about normal C arrays. It's really easy to override some memory when using them, so we will here create an own array class which eliminates all the array related issues. and then we will take a look on templates, how they work, and implement a few template functions. And then I think we will implement an own smart pointer, since at this point we will have all the utilities needed to do this. And if time is left, we will even take a look on C++ exceptions. Since we have already taken a look on C exceptions, C++ exceptions will be rather a very short topic, because it just adds a nice twist to what you could already do with exceptions, and a nice level of customizability. Okay, so that's that. We will see each other next week. Have a nice weekend. Bye bye.